Hello to everybody. This is the 10th lesson of algorithmic design, and just a little bit recap to remember what we did the last time. So during the last lesson we introduced the sorting problem. We saw an algorithm named insertion sort, and we prove its complexity, which was big O of n square, the worst case, and in the best case omega of n. Then we move to a different algorithm named Quicksort, which basically partition, select a pivot, so select an element in the array, and partition all the elements of the array itself by moving all the elements which are smaller or equal than the pivot at the beginning of the array, and all the elements which are greater than the pivot at the end of the array. And by repeating this procedure, this operation, until we end up with frames of the original array whose size is smaller than 2, we basically perform the sorting of the array itself. And we were dealing with its complexity. And to deal with its complexity, we introduce a recursive equation in which we basically prove that the complexity of executing quicksort on an array depends on the complexity of executing quicksort on the first part of the array, plus the part of the array which maintain the elements which are smaller or equal than the pivot, plus the complexity of executing quicksort on the second part of the array, plus the cost of partitioning. We introduce a procedure to, well, we saw an idea to partition the original array, and we guessed its complexity, which was theta of n, but we miss to see the code of partition procedure itself, and to better evaluate, so to prove that the complexity of the idea we had, it's actually the one we guessed. So to start the lesson today, we will see the code. We will have a brief recap of the intuition of the partition procedure we want to implement, and we will implement the partition procedure itself. Okay, so let me move to the whiteboard, just to remember you what's going on with the partition procedure. So let me write partition procedure, okay. So what's the idea behind the partition procedure? Well, the idea is to deal with an array, of course, or better with a frame of an array, so a part of it, a chunk of it, a contiguous part of it. So let's say I want to deal with well, let me say I want to deal with all the array, just to avoid any misinterpretation of what I'm saying. Well, of course, this is the array A, and I want to deal with a pivot. So let me assume I'm dealing with this pivot. So the pivot has been selected in any way. Okay, you can choose any possible way to select the pivot. It doesn't matter. But of course, to partition the array, you need to have it. So the first step, so step number one was to move the pivot at the beginning of the array, at the beginning. for instance by swapping it. Okay, so the very first step is to swap the pivot with the first element of the array. Okay, so now the pivot is no more here, that's been moved to the first element. So let me redraw A. So after the first step we are in this situation. This is the pivot and this is the array. Okay, now we can use two different indexes. The first one is I, and I will basically tell us where we can put the next element in the first part of the array. Okay, so up to I minus 1 everything has been already proceeded, and so what is missing is for sure from I on until J. So J is an index telling us where the next element greater than the pivot should be placed. Okay, and so at the beginning I will be 2. What's going on here? At the beginning I will be 2 and J will be length of A. What's going on here? Okay, anyway, so this is the situation. So so the second step is to test whether step 2. So the second step is to test whether if I is greater than P, well, AP of the, sorry, let me say in this way, A1, which is pivot. So I'm testing whether the element in position I is greater than the pivot, and if this is the case, well, the element pointed by I should be placed at the end, so I can simply swap AI and AJ. So if this is the case, I'm moving the element in this position here and the element in this position here. Okay, I'm swapping them. Okay, so once I swapped them, for sure the element pointed by J is greater than the pivot, because I decided to move it because it was greater. So once I swap the two elements, the element in position J should be greater than the pivot, and then I can decrease J and decrease and decrease and decrease. J. Okay, so this J now is here. Okay, if otherwise, and so let me delete this. Oh, too much. And this. Okay. If otherwise, So otherwise means if the element pointed by I is not greater than 1, that means that the element pointed by I is smaller or equal than the element pointed by 1, so the first element in the array, which is the pivot right now. So something is wrong with my tablet. Anyway, what can we do? Well, we can increase AI by 1, increase I. Why? Because this element, so the element pointed by I is more or equal than P, so basically should be inserted in the S subarray, so the subarray maintaining the elements smaller or equal than the pivot itself. So we can basically increase I, which is the next element to be included into the partition, the first part of the array. Okay, and of course we need to. So step 3. Repeat 2 until what? Until let me go back one slide. Until I surpass J. So until I is so while I is smaller or equal than J, there are something which hasn't been processed yet, so we need to going on with the processing. So until I is greater than J. So we stop our iteration, the execution of this operation, sorry, not I but J, of course, here. The first time we see with condition, okay? And the first step we need to perform, step 4. So at the end of everything, we will be in this situation. We will have the partition, the pivot at the very first element in the array, or better in the frame we are dealing with, and here we will have J, and here we will have I, and if this is the case, we have to so everything from here to let me see, from here to here is S, everything from here to here should be in G. And so right now we have to move back the pivot in its position, and to do it we need to swap P and J. So the first step is to swap A1 and AJ. Okay, so by swapping these two elements, we end up in a situation in which all the elements smaller or equal than the pivot are at the beginning of the array, all the elements which are greater than the pivot are at the end of the array, and the pivot is in its correct position. So these are basically all the 4 steps we need to perform. Let me now write the code, and let me use all variable we already saw. So the partition will be this one, the procedure will be the procedure partition, of course, partition, and the partition procedure we will take the array A, and well, let me see, Okay, but by the way, as usual, let me know whether you can hear me and I'm online, just to be sure. So I was saying the partition procedure is called partition, of course. It will take the array A, it will take let me write in this way, lower bound, so no lower bound, a left bound and a right bound, meaning I want to deal with the frame going from L to R, and of course the position of the pivot. Okay, and this is it. So the first thing to do is to move to swap in A, P and L. So okay, now let me assign at the same time, just by using a not really appropriate notation, let us assign at the same time I and j. So I will be L plus 1 and j will be R, of course, and this is it. So while I is greater than j, so smaller or equal than j, sorry, then we have to process a part of the array. So how can we do it? Well, by testing the element in position I. So if ai is greater than L, which is right now the position in which we place the pivot, then if this is the case, then we have to swap the element in position I and the element in position j. So swap A I j, and of course right after the swap the element in position j is greater than the pivot, so we can do else. We can do, oh no, not else, of course. So we need to decrease j, of course. So j would be j minus 1. Otherwise, so if the element in position I is more or equal than L, of course it should be included in S, so we increase I by, let me write I as usual, so I by 1. We increase I by 1, and this is it. And if well, let me move to the next page, and well, and while and so basically right now we implemented all the while, so we have to do something after this condition stops to hold and it doesn't hold anymore. So what should we do? So if this condition doesn't hold anymore, so we have to move the pivot in position j, which is the last position of the elements in P. So swap A, L, and so J. Swap. And this is all. So and if and def. Okay. So this is the the definition of, so this is the pseudocode of our partition procedures, and that's it. Now let's try to figure out the complexity of this procedure. The first part, of course, takes time theta of 1. Okay, so these three operation takes time theta of 1 because swap takes time, it takes a constant time, and these two assignment, of course, take a constant time. So the overall cost of the first part of the array is the first part of the procedure, of course, is theta of 1. Now, what's the cost of the while block? So what's the cost of executing this operation? Well, the cost of executing the swap and the assignment is, of course, theta 1. The overall cost of the if conditional statement, of course, is again theta 1. So the cost of the while loop of the while block is theta 1. No repetition, all the operations are performed in constant time, so theta 1. What about the number of iterations we are required to perform for the while loop? Well, this is quite easy to see. Why? Because at each iteration of the while loop, we are decreasing the distance among j and I. Okay, and again, we can prove it, but it's straightforward to see. So either the element we are considering in position I is greater than L, and then we decrease j, or we increase I. So eventually we end up in a situation in which this condition doesn't hold anymore, but the number of steps we are required to perform is actually the number of steps, the distance among j and I at the beginning of the iteration. Since since I is L plus 1 and j is R, the complexity of executing this while loop, so the number of iterations we are required to perform to execute this, to perform all the possible iterations of this while loop is, of course, theta of R minus L. Okay. Repetition. Okay, so again, why? Because at the beginning of the computation with this while loop, j is R and I is L plus 1. So the distance among j and I at the beginning of iteration is R minus L plus 1. And of course, this is in theta of R minus L. Okay, and let me see. This is it. Of course, okay. Of course, this is this cost theta of 1. So the overall cost of the partition procedure on a set of an element. So on an array having an element is theta of n. Okay, n is the, so where in this case n is equal to R minus L. Okay, this is it. So let me move to the slides. So this is the complexity. So what's the complexity of Quicksort? So Quicksort complexity. So the complexity of Quicksort will be T. So let me rewrite the equation we saw. So the complexity of performing Quicksort on an array of length A is the complexity let me avoid the constant time execution, so let me consider exclusively the recursive step, let's say. So will be, of course, the time to execute quicksort on array of length A will be the time to execute quicksort on the array of length S, plus the time to execute quicksort on the array of length A, so on the array A minus, of course, S, which is the first part of the partition, minus 1. This is equal to basically the length of G, plus, well, here we need to place the complexity of the partition procedure, which we saw is theta of length of A. Okay. So this is basically the complexity of quicksort. So now let me evaluate the real complexity. So this is a recursive equation, but we need to have it in closed form. So how can we do it? Well, let me consider worst case scenario. So in the worst case scenario, so in the worst case scenario, the length of S is 0. Why? Because we at each iteration of our quicksort algorithm, we are selecting as pivot the smallest element in the array. Okay, and there are no repetition. So in this case, well, or of course G equal to 0, which is symmetrical. In this case, this equation becomes length. So worst case scenario, this equation, the above equation, becomes Q length of, let me select this case just to know. So this is 0 plus and TQ, and so if S is 0, this is basically length of A minus 1 plus theta of length of A. Okay, this is of course equal to theta 1. We already know it, and so if we unravel basically this equation by induction, we end up in concluding that this equation belongs to well, let me do all the steps just to avoid any confusion. This is basically just as equal as summing up I going from 0 up to length of A of I, which of course is equal to this is theta, which of course is equal to theta of well, since we are dealing with the worst case, let me move to big O notation. This is big O, and so this is square minus, no, this is I multiplied by I plus 1 divided by 2, which of course is belongs to big O of I square, no, not I, I'm messing up everything here. So this is length of A multiplied by length of A plus 1 divided by 2, which of course, and now let me delete in the, just because I need more space, this is of course length of a square. Okay. Yeah, I'm writing big O because I'm dealing with the worst case scenario. So if I assume the worst case scenario, I'm in theta notation, while in the general case, I only can say that this is the worst case scenario, but it could be better, and we will see why. Okay, so the worst case scenario is when either S is 0, the length of S is 0, or G is 0. So if I select as pivot the largest element in the array or the smallest element in the array, I end up every steps I end up with a quadratic algorithm, which basically is equivalent to the insertion sort algorithm. Okay, so quicksort in the worst case is as insertion sort, nothing but better. What about the best case scenario? So the best case scenario, well, not the best case scenario, but the best case scenario, yeah. Best case scenario. Well, the best case scenario is a scenario in which we are guaranteed at each step to partition the array in two subarrays for which the ratio among the length of the two subarrays is above a given step. So, for instance, let's assume we are so lucky to be guaranteed that the partition procedure split the array into two subarrays whose size is at each step 1 and 1/10 and 9/10 of the original array. So let me consider the case. So at each step the length of S is 1/10 of length of A, and G is 9/10 of the length of A. Of course, by length of A, I don't mean the length of A at the beginning of computation, but the length of the frame I'm dealing with at each recursive call. Okay. So in this case, I can build up the tree, the recursion tree, and so, well, let me write it. We know that the partition procedure takes time, which is theta of n, so I can use a representative of theta of n to write my tree. Let's say I want to represent theta of n by using c multiply n. Okay, so this is the cost of performing partition on the overall array. Then I need to perform quicksort on S and quicksort on G, and this can be done by two recursive calls. So the first recursive call, of course, will need to perform partition, but will perform partition on 1/10 of the original array. So this is it. And of course the second partition, which is G, will perform again the partition procedure on 9/10 of the original array, which is, should be n, of course, which is 9/10 of n. And again I can go down one step further. So once I perform partition on this part of the array, I need to perform partition on its S subarray, and its S subarray takes time. Takes time 1 over 100n. And what about its G? Well, its G will be, of course, 9 divided by 100n length. Will have, so G will of this frame of the original array will have exactly 9 divided by 100 n elements, and the partition on this subarray takes time. C multiply that number. So what about the subarrays S and G of this frame? Well, also for this frame we will have an S which will be 1/10 of the original array, which of course will be 9 divided by 100 n elements, and the cost of the partition of this particular subarray will be C multiplied the number of its element. And of course we are missing the G subarray of the the original array, which of course will be 9/10 of this subarray, and so 81 divided by 100 n will be its length, and the cost of performing operation here will be C multiply this number. Okay, and so let me move to the next. Now you understood what's going on here. I don't want to build up all the tree, but just to let you know how it's going on. So at some point, so the leftmost branch of the tree will end up with a 1. Okay, while with a 1, no, not a 1, but a C, of course, I'm sorry, a C, and the rightmost branch, of course, will end up again with a C, but will be much longer, as you can guess by looking at this level. So in this level we can see that the rightmost branch decrease much faster than the leftmost branch of the tree decrease much faster than the rightmost branch of the tree, and so of course this is it. And okay, now let me guess the height of the leftmost branch of the tree. So the height, let me write in this way, and here, okay, oh, wrong page, this is it. So the height of the leftmost branch of the tree will be due to the speed in which we are decreasing n, of course. So at each level we are decreasing n by 1/10. So we are dividing n by 10. So basically here we are guessing the logarithmic 10 of n. Okay. So the number of steps required to reduce n to 1 is of course the logarithmic base 10 of n. What about the right branch of the tree? Well, the right branch of the tree has more or less the same situation. Oh, let me use a different color just to understanding what's going on here. So let me use the blue one, for instance. So this is it, and this is it. So again, here we are basically decreasing n by, we are dividing n by 10 divided by 9, okay? So here we need to find the logarithm base 10 divided by 9 of n. So how many steps are required to get from n up to 1, dividing n by 9/10? Well, of course, is the logarithm base of base 10 divided by 9 of n. Okay? So now we know that both the right side and the left side, of the tree has a height which is logarithmic with respect to the logarithmic with respect to the ratio between the length of S and the length of G. So let me answer just right now to some of your question. Why the best case scenario? I remember using consistent already order array. So someone is asking, the best case scenario is not shouldn't be the one in which we have already an ordered array. Well, no, is not this the case. This is the case for insertion sort. So for insertion sort, the best case scenario is to have the already ordered array, an already ordered array. But in this case, this is not the best case scenario, because of course we need to deal with the pivot. So we understood that by going, let me go back to the worst case scenario. We understood that in the case in which S or G are equal, the length of S or the length of G are equal to 0, the overall complexity of Quicksort is quadratic. Okay, and this is quite easy to see. So if you just try to figure out what's going on if you always choose the smallest element in the array. So you choose the smallest element in the array, you need to go through all the other elements to evaluate the partition procedure, because there's no way to guess that the elements are not in the correct position. And then once you have performed the partition, which takes time theta of n, you have to call back Quicksort on the two subarrays S and G. But of course, since S is empty, all the elements which are not the pivot itself end up in G. So the length of G is the length of A minus 1 as we saw it, and the complexity is quadratic. Now, now we are seeing that this is not the case for the best case scenario, and of course this means that the choice of pivot actually matters, as you correctly understood. But the point is that whenever you so if you don't use any knowledge about your arrays, and you blindly choose one pivot just by selecting a specific strategy to select the pivot, but blindly with respect to the array you are dealing with. So for instance, by choosing, I don't know, the third element or the last element of the array or the first element of the array, if you do it blindly, you end up with again a quadratic worst case scenario. So whenever you select a pivot inside the array blindly, I can provide you with a counter example which proves that your strategy will end up with a quadratic algorithm. Okay. So let me go on with best case scenario computational evaluation. So we saw here that the height of the tree, of the branches of the tree, are in any case logarithmic. So in the best case scenario, in which we are dealing with a ratio among S and G, which is 1/9, we end up with a situation like this one, and for all the branches we are guaranteed the branches are logarithmic with respect to the size of G. Now let's try to evaluate the complexity of performing level by level all the partition procedure. So the partition procedure at level 1 takes time C and wrong color. So the partition procedure at level 1 takes time Cn. So the partition procedure at level 2, so the total cost of the partition procedure among all the subcalls of where this is happening. Something really weird is happening. I don't know whether you are still there, so please let me know. Please let me know if you are there. Okay. Okay, in any case, this is the worst case scenario as we saw it. This is the computation for the best case scenario as we saw it. Now we have to this is the computation. Now we have to evaluate the probability of getting a good, now it's working, okay, great. We have to get the probability. I was evaluating the complexity of the best case scenario. I don't know where I lost you, to be honest. And I was answering to your colleague probably, and I was saying that the selection, the position of the pivot is actually, well, the selection of the pivot is actually relevant, but whenever you choose the pivot in a blunt way with respect to the array, you end up 10 minutes. Oh, that's awful. I don't know why. Anyhow, I was saying that the worst case scenario. Well, I was saying that the selection of the pivot is relevant, but in any case, whenever for any possible strategy, blind strategy with respect to the elements in the array, you choose to select the pivot, you end up with a quadratic algorithm in the worst case. So the worst case will be quadratic. As a matter of fact, I will find out for any strategy you choose, I will find out a counterexample which will end up with a quadratic cost. However, in the best case scenario, we understood the complexity of Quicksort is theta of n log n, which is promising. So what's the probability of getting, and you will find everything on the slides, and I will publish also the whiteboard, so probably that will be enough to cover the 5-10 minutes you lost during the lesson. Or it could be also the case that the stream wasn't lost, so you may have a look to the recorded lesson on YouTube. However, now what's the probability of getting a balanced partition? Oh, by the way, we are missing the average case. So what if we have a good partition, and then a worst case scenario, and then a good partition, and then a good worst case scenario during the recursive call? So what if a given level I get a worst case partitioning? So during a call I discover that S is empty, and then after that I discover that I'm dealing with a good partition for G. Well, in that case, but this is the probability. Sorry, I swapped the two topics. So the probability for good case is the one you can see here. So if the ratio among S, the length of S and the length of G is 1 divided by N, so the probability of getting a partition which is more balanced than the one described by this ratio is this one. Okay, of course, but only if we assume that all the permutation of A as equally likely. Okay, so you can try to figure out why this is it, but I mean that's the case. So if you want to get a partitioning in which the ratio among the length of S and the length of R is greater than this case, than 1/9, then you can get it with probability 8 divided by 10. Okay, and this is it. Now, what if we end up in a situation in which at one level the partition procedure end up with an empty S, and then at the next level the partition is good? Well, here you can see what's going on. So at this level, in this tree, we are depicting a situation in which this level S is empty, while all the elements went with G, of course, all the elements but the pivot went with G, and then at this level we end up with evenly partition of G itself. Okay, so this is the tree. But if I basically sum up in a weird way, let's say, the recursive call, well, not recursive call, but the cost of the partition for this level and this level, I end up with a cost which is of course theta of n, because it's twice of n minus 1, and this branch doesn't matter because it's empty, so I'm left with evenly partition part of the array, which is exactly what I got in the case of a lucky partition, let's say, a best case scenario, which is basically a proof that if I alternate good and bad cases, I end up with, again, theta of n log n algorithm. Okay. Now this is good because we discovered that there are algorithms for which which perform better than insertion sort in the best case scenario. So it is possible to do something better than insertion sort. But actually, if you better look at the situation, insertion sort still outperform Quicksort, because in the best case scenario we get a linear complexity with respect to length of the array, while here we are getting n log n complexity. However, the probability of getting the best case scenario for insertion sort is rather low, because to get the best case scenario you already have to deal with a sorted array. So you have one chance over the factorial of n, which is the number of possible permutation of A. Okay, so you really need to be quite lucky to get the best case scenario for insertion sort, and since I'm not really lucky, I get stuck with a quadratic algorithm by using insertion sort. While in the case of Quicksort, although the worst case complexity is quadratic, just like insertion sort, the probability of getting a good case, let's say, scenario, not the best one probably, but a good case scenario, is quite high. So and we can evaluate it actually. And so if you want to bet for a good performance, for sure Quicksort is much better than insertion sort. Okay, so while the complexity, the overall the best case, worst case scenario perform much faster, insertion sort perform in worst case scenario much faster than Quicksort, the probability of getting a good scenario in Quicksort are much higher than with respect to the insertion sort algorithm. Okay, so that's why Quicksort could be a good choice with respect to insertion sort, but we will see it probably. Well, you will see it doing your homework, because I will request you to implement both of them. Okay, not for this lesson, but the next lesson. So tomorrow I will give you some homeworks about the sorting algorithms. So let me move to the next topic, while for sure we will not be able to conclude it. And the next topic will be finding the maximum. So again, we are dealing with the sorting algorithm, but we are trying to find a different strategy. So up to now we saw insertion sort, which try to increase the size of the sorted part of the array by inserting element at the beginning. So the sorted part of the array is located at the beginning of the array itself, and we keep inserting the elements inside the sorted part of the array by swapping, pairwise swapping the elements. Of course, this strategy is nice, we saw it, but we may try to find a different way to sort, and in particular a way which avoid to perform all these swaps inside the already swapped part of the array, and the strategy is based on finding the maximum. So let's consider this situation. We are dealing with an array, and this is the maximum, and so a possible way to sort this array is to find the maximum and place it at the end. Okay, and this is it. So right now we have a situation in which the first part of the array is not sorted, while the last part of the array is sorted, because we have inserted the largest element in the array, so the greatest element in the array, and for sure this is the correct position for it. Now we can repeat all these steps by finding again the maximum. So this is what I said. So we can repeat what we did until now. So search the maximum among all the elements which haven't been sorted yet, and place it just in front of the sorted element. Okay, since what it is greater than it was already placed at the end of the array A, for sure this element should be placed before them. And since it is the greatest element among the unsorted part of the array, this should be at the end of the unsorted part of the array. So by selecting the maximum and placing it at the end of the unsorted part of the array, I'm able to grow the sorted part of the array and decrease the unsorted part. And by repeating all these steps, of course, I'm able to sort the array itself, and as you can see here, I'm not swapping the element in the sorted part of the array. Okay. Now, what's the complexity of performing all these operations? Well, the complexity of performing all these operations is of course the complexity of searching the maximum, which is T max I. So the maximum among the ith element which hasn't been sorted yet. And this is the complexity of searching the maximum, and we will see how can we do it, plus the complexity of basically moving the maximum at the end of the unsorted part of the array, and this should be performed for all the length of the unsorted part of the array, which goes from the length of the A itself, so the whole array, down to 1. Okay, so this is the complexity of this strategy. Let's see whether this strategy can outperform both insertion sort and quicksort. So the point right now is how can we find the maximum? Well, a possible strategy is by pairwise swapping the maximum to the right, and this ends up with an algorithm called bubble sort. So the idea is just like the bubbles inside a glass of sparkling waters. The largest bubbles goes to the surface quite faster than the small bubbles. So this is the idea basically. And so the first thing we have to do is to test whether a certain element, so the element in position j, is greater or equal than 5. If it is smaller than 5, so the next element to him, well, we simply increase j, okay, and we pass to the next. So here we are testing whether 5, which is the maximum among the already considered elements, so 5 is the maximum among 0 and 5 itself, of course, and we are testing whether this is smaller or equal to 7. So if this is the case, so if 5 is greater than 7, and this is not the case, then again we move on, because we discover that 7 is the maximum. So now we need to test whether 7 is greater than 2. If this is the case and this is the case, we need to swap them, okay, and so now j is 7, is pointing to the 4th place, so it's pointing to 7. And again, we need to test whether 7 is greater than 4. If this is the case, we need to swap them, okay. And after a while, we end up in a situation in which the maximum among all the elements in the unsorted part of the array end up in the last position of the unsorted part of the array. And so let's see the complexity of all this procedure, and to do it we need to write the code. So let me just save quicksort, okay, and let me go back to the whiteboard. This is the whiteboard, and this is it. So let me write bubble sort. So bubble sort, is quite easy. Of course, we'll take A, and so the array we are dealing with, and we want to, what's going on is really annoying. Okay, so the first thing to do, we have to scan all the we have to scan A from the right to the left. So for I in A, A up to, and let me write here 1. That's okay. So I will be the position in which I want to insert the maximum. Okay, and then for all the possible j going from 1 up to I minus 1, I'm testing whether aj is greater than aj plus 1. If this is the case, I swap aj with aj plus 1, and that's all. Okay, and 4 and 4 and f. And this is bubble sort. Okay, so I will be the position in which I want to place my element. J will be the position containing the maximum element found until now in my array. Yeah, and whenever the next element with respect to j is smaller than j itself, I swap them. So right now the maximum is j plus 1 because of the for loop. At the next iteration j will be j plus 1. Okay, and that's all. So what's the complexity of this algorithm? Well, the complexity of this block, so the conditional statement, is of course theta of 1. The complexity, the number of iteration, the number of repetition of this for loop is of course theta of I. And so the overall complexity of bubble sort, let me write it, complexity of bubble sort, complexity of bubble sort so the complexity of bubble sort will be, of course, so for each iteration of this for loop, and let me write it in this way, so I going from 1 to a, and simply reversing the indexes. It doesn't change anything. I need to perform I minus 1 repetition of what? Of theta 1. Now if I perform all the computations, I end up with a theta of, this is theta of course of length of a square. So bubble sort is quadratic, even in the best case scenario. Okay, so bubble sort is worse than insertion sort, worse than quicksort. So that's not what we are searching for. Let's try to find a different. Oh, this is not where I was. I'm missing it here. So let's try to. This is the bubble sort complexity in the code and whatever you are searching for. So let's try to find let's try to find a different strategy. A different strategy which basically search the maximum by using a linear scanner. Okay, so the idea is to scan all the unsorted part of the array, try to find the position in which we have the maximum element among the unsorted element, and then at the end I swap it with the last position of the unsorted part of the array. So let's see. We start from the very beginning of the array. We at the beginning the maximum of the elements would be in position 1. At this point we should be moved in position 2. At this point should be is in position 3. Then I get an element which is smaller than the previous one, so I'm not replacing it, and so on and so forward. After a few steps, I know that I end up with the last position I'm dealing with, and I need to deal with, so the 8th position. The maximum was found in position number 3, so by swapping them, I end up in a situation in which the maximum is now at the end, and I can grow the sorted part of the array, and the unsorted part of the array is decreased. Okay, so the situation is quite clear, and so let me write the code of this stuff. This is bubble sort, but I need to write something else. Okay, so by the way, the name of this algorithm is selection sort. So we are selecting the maximum among the elements which are not sorted, and then we are placing it at the end of the unsorted part of the array. Okay, so this can be done in this way. So def selection sort, and of course the parameter is the array A we want to deal with, and so I need to say where to place my element, and this is done by using a for loop which goes from length of A up to 1. Well, it's not really needed to go up to 1. It's just needed to 2 would be enough. But let me use 1 just to avoid to deal with the difference in the complexity. Okay, and okay. So now right now we have to set a variable containing the position of the maximum among the already considered element, and at the beginning will be 1. So maxj will be the index of the maximum element among the elements in the array, the unsorted part of the array. Okay, so for j in, and here let me write 2 in A2 up to A. What's going on here? If aj is greater than A max j, well, max j will be assigned with j. So if this condition holds, I've just discovered an element which is greater than the element which I thought thought to be the maximum among the elements in the unsorted part of the array. So I need to assign my j to assign j to max j, and this is it. And if and for and so, well, this is an error. This should be, of course, I minus 1. Okay, and not I minus 1, but I actually, because I need also to test whether the last element, the element in the position I want to insert the element, insert the maximum, is greater or equal than the previous one. So this is the correct range for the 4. And once I end up all this computation, I need to swap the maximum element, which is contained in index max j, with the element in position I. So this is it, and this is an and4, and this is an and def. So let me see the complexity. So what's the complexity of this block? The complexity of this block, of course, is theta of 1, because I'm performing a constant number of operation. This swap costs theta 1 again. This assignment costs theta 1. So the overall cost, okay, so how many times I'm repeating this 4? This 4 has theta of I repetitions. And while this, of course, has theta of length of A repetitions. Right iteration. Okay. So let me write the complexity then. So the complexity of selection sort among an array of length A is the sum for I going from 1 up to length of A, or the sum going from j from 2 up to I of what? Of theta of 1, and this plus theta of 1. This is due to the swap, of course. So if you perform all the computation, you end up in a sum of length of A, and this is, of course, theta of I plus length theta 1, and again this is theta of length of A square. Okay, so again, the complexity of selection sort is worse than the complexity of insertion sort and the complexity of quicksort. So this strategy doesn't seem to be good enough to deal with sorting. The idea was nice because the idea was to avoid swapping on the certain part of the array, but at the end doesn't help. And as you can see, even in the worst case scenario, we end up with a quadratic algorithm. So is there a different possible strategy? So it is possible by using this this idea of selecting the maximum among a bunch of unsorted array, unsorted element, and keep moving it at the end of that unsorted part of the array to sort the overall array. So it is possible to find a way to find the maximum among the unsorted part of the array to decrease the complexity of this of the sorting procedure. Okay, so the question is this one: are we able to find a strategy for finding the maximum which allows us to sort the array in less of length of array square number of steps? So this is the question for you for the next lesson, which will be tomorrow, and of course there will be a positive answer, but please don't look at the slides, simply try to figure out a possible way to do it. Okay, this is the homework for you, and we will see it tomorrow. So thank you for the attention. I'm quite sorry for the problems you faced. I don't know why the video dropped. Probably I had a problem with my line, but I wasn't able to see it actually, and this is it. So thank you for the attention. Again, try to figure out a possible strategy to find the maximum among the unsorted part of the array to sort the array, and see you tomorrow then. Thank you. Bye.